Hi everybody. So in this video we're going to look at modelling real-life problems using a volume of revolution. So in this example, we're told that Dr. Rutherford constructs an ornamental mushroom for her garden from an old tree trunk, and she approximates the mushroom by modelling it as the solid of revolution formed by rotating the region 2 pi radians about the y-axis. And the purple region is bounded by the x-axis, the lines x equal 2, y equals 2, and the equation y equals 6 minus 0.4 x squared. Each unit on the axis corresponds to 10 centimeters, and we've been asked to use this model to estimate the volume of the mushroom to 2 decimal places. So to begin with, because we are revolving around the y-axis, we're going to use the equation where the volume is pi multiplied by the integral between the range a to b of x squared dy. And there's two parts in this volume. There's the cylinder on the base and the curved volume on top. And the limits of the curved volume are between y equals 6 and y equals 2. So the first thing we're going to do is find the volume of this curved solid. And we're told that the equation of this line is given here. I'm going to convert that 0.4 into a fraction. So we get y will equal 6 minus 2/5 of x squared. And we need to make this x squared the subject. So we'll move all of this to the left hand side and the y to the right hand side. So we'll get 2/5 of x squared will equal 6 minus y. We can reciprocate this 2/5 to the right hand side. So x squared will equal 5/2 multiplied by 6 minus y. And then we can substitute this expression for x squared into our equation. So the volume will be pi multiplied by the integral between the limits of the 2 and the 6 of 5/2 times 6 minus y, integrated with respect to y. And because this 5/2 is just a constant, we can move this out in front of our integral. So the volume will be 5 pi over 2 multiplied by the integral 2 to 6 of 6 minus y dy. And then we can integrate this. So the volume will be 5 pi over 2. We integrate the 6 and we get 6y. We integrate the y and we get 1/2 of y squared between the limits of 2 to 6. Now we can substitute in our limits. The 6 times 6 will give us 36. And then half of 36 will be 18. So we'll have the volume 5 pi over 2, lots of 18. We'll substitute in the 2. We get 12 minus a 2, so 10. And then we can multiply this 8 by the 5/2. So our volume will be 20 pi. And this is in units cubed. So we've worked out the volume of the solid on top. Now we need to work out the volume of the cylinder. We know the height is from the x-axis to this point. So we have a height of 2. And the radius is from the y-axis to this point. So the radius is also 2. And we know the volume of a cylinder is pi r squared h. So we'll square the radius and we'll get 4. We'll multiply this by the height. So the volume of a cylinder will be 8 pi units cubed. Now we can add these two sections together. So the volume of a model will be 28 pi units cubed. And we're told that each unit on the axis corresponds to 10 centimeters. So we can write the ratio as the volume of a model to the actual, which is 1 to 10. This gives us a length scale factor of 10. What we need is the volume scale factor because we're dealing with this volume. We know that the volume scale factor is the length scale factor cubed. This will be 10 cubed or 1000. So the actual volume will be the 28 pi multiplied by 1000, which gives us 28,000 pi centimeters cubed. And to 2 decimal places, this is 87,964.59 centimeters cubed. Okay?